How do you graph lines? You're going to draw. Thanks. I was being nice and not on you. Dope. What's the one way that you graph lines? Linear equations. 2 points and draw it out. Okay. Or that's called slope-intercept form, right? Point slope stuff? Yeah, that's when you're given 2 points and you have to write out the equation, find the slope and all that. Yeah, you can do all that. More or less, right now, we're not going to see that much of this. But we had what was called slope-intercept form, which you guys all know. And slope-intercept form is great because the y equals button, there's a y equals button. You can graph it. There's a lot of stuff you can do. You can make tables, you can do all that kind of stuff, and go from there.
There's something that has like an x and a y and an equals something.
Jeez Louise.
I didn't like geometry, okay?
Hey, you have a sister, Jared?
No, that's my first name.
Wait, I didn't know that. What's your first name?
I do.
So wait, what's his first? Wait, what?
Wait, right now?
I'm so confused. Awkward moment. Wait, what's your first name? His name is Frank. Rizzo. What's up?
Jared.
3. 4. I don't know what's it say.
Is it Jared?
Hey, buddy in the black shirt. Yes. Is that what it says? Go now?
It just says.
Wait, when do we have to go to those?
And what is it? I don't know.
Do we have to?
Anyway, what's his name? He was calling him a girl. What's his name? Have to tell him. What was that called? Sue. There was a boy named Sue. Standard form. Very good. This was called standard form. The standard form, when you're using standard form, you're able to do a couple of different things. It wasn't very useful when you guys learned standard form back in Algebra 1, because most teachers would always tell you to put it into slope-intercept form. You basically move standard form around and solve for y. Do you vaguely remember that?
Yeah.
Well, what I'm going to tell you right now is just going to show you that standard form is really, really, really nice because you can graph out a standard form in one step. Ooh. I know, it's crazy. But wait. Let's do this. So if I have 4x plus 2y is 8, that would be standard form. Do you agree? And if I wanted to graph that, I would normally sit there and go through and solve for y and do all that stuff, find my slope, find my intercept, and mark things out.
Why?
Exactly.
There's more.
But wait. What we can do here is use what are called intercept forms. When you have your y-intercept is when x is equal to 0. You agree? Yeah. So if I cover this up, what's your y-intercept? 4.
Oh, well.
What I'm doing there is I'm letting x equal 0. So I'm covering it up, and I'm getting my y-intercept.
Oh, okay.
Does that make sense? Yeah. Now if I cover up the y, that gives me my value for y is 0 at the x-intercept. So what's my x-intercept? There's my 2 dots, like Michael was saying, and connect them. And you graph it.
It's magical.
It's called quick graphing. It is a very efficient way to do things just by cover and solve. All you're doing is you're covering up by covering it, you're saying that the x value is 0 or the y value is 0 and you're finding the x or the y-intercept then. Very, very easy. The other thing that we did is when we graphed stuff, we talked about graphing inequalities. For example, if I had 3y plus 2x is less than 18. If I wanted to graph that with an inequality, there's a little bit extra work to do. Again, it's set up in that nice standard form, so we're going to do that cover and solve. Yeah, it's along those lines. And notice, I'm not using graph paper. You don't need it. You don't need it. Okay. So cover and solve. What's your x-intercept?
9.
9. What's your y-intercept?
6.
Now it's a less than problem, so when I connect those, it's going to be a solid or a dotted line. It's dot. Remember that? What's that? You can do that if you want. But this one, this is, what I'm saying, my x-intercept is still going to occur at the, or my y-intercept, they're still going to occur at those values. It's the actual line itself becomes what we would consider an open circle, all right? Because it's still going to be at that value. I mean, the intercept would go through that. But yeah, I know what you're talking about. It's okay if you put the solids in. It's not a big deal. I almost stabbed you in the face. I'm sorry. Because I went up like this as you walked by. I know. I'm all psycho.
That's on tape.
Psycho movie.
I know.
No, you don't. You
Well, like the tape, you just hear I'm psycho, and I just try to stab you. So,
Anyway, when you're dealing with these things, you have to have what's called a shaded region. So you have to pick a point that's not on that line to see whether or not it's shaded towards it or away from it. What's the easiest value to choose? 0. So what's 0 plus 0? Is 0 smaller than 18? So it's everything going this way. So your shaded region would be on that half of the graph. You can shade it if you want, that's fine. It's not a big deal. Either way is fine. Okay? What's that? That's okay, shade it. It's not a big deal. It's not a big deal.
how do you pick which side to shade?
You just pick a test point. Remember, what's happening here is that the graph creates what's called a half plane. It cuts the XY grid in half. And then you're just checking to see, is it true or false on either side? The easiest point to check if your line doesn't go through it is 0, 0. So you're just substituting 0 for both x and y and see if it's true or false. So if it was false, I would shade on the other side. And if it's true, I shade towards it. You want to cover up the truth, because you can't handle the truth. Take a minute and shade out these 4. Take a minute and shade out these 4. What changes now when you're putting 2 graphs on 1 graph paper is just that. You're just putting 2 on 1. That's all. You're looking for a shaded overlap. So when you plot it out, these guys happen to be in slope intercepts. You just walk it through. It doesn't have to be absolutely perfect, because you're going to make it look as best you can.
Wait.
Anyway, so in this case here, if I just go to slope intercept for my first equation, my intercept is at 3. You guys okay with that?
Yeah.
Slope is -3, so I go down 3 over 1, down 3 over 1.
Why are you doing down to
What's my slope? It's -3. So that means your slope is -3 over 1. Okay.
I don't remember this at all.
Oh boy.
Can you go over why
Rise over, yeah,
The y equals mx plus b?
Yeah, but yeah, this is like,
Your y equals mx plus b. M is your slope. This is your y-intercept. Okay. So the coefficient in front of the x is your slope. In this case, the coefficient was -3, which means it's -3 over 1. What's that?
oh, I got it.
And remember, slope is change in y over change in x. So it's rise over run. So in this case, your slope, you move up and down first before you go left and right. So you move down 3, right 1, down 3, right 1. And that's all that works out. Okay. So now from there, pick a point. Does that go through 0, 0? No. So is 0 smaller than 3?
Yeah.
Yes. So we shade on that side. You okay with that? I graph the other one. My other equation is y is greater than x minus 1. What's my y-intercept? And what's my slope? 1. So I go up 1, over 1. Up 1, over 1. Up 1, over 1. And when I connect those, will it be solid or not? Dotted line.
Whoa, how do you decide what's up or down? 0.
Again, you pick a point that's not on the line. Does 0, 0 go through that on that line?
No.
So is 0 bigger than negative 1?
Yes.
Yes. So the shaded overlap region is there. Is in this section here. Okay.
I knew doing, you have to get double shaded.
No, because you'll see how it's double shaded out as you start to graph it. When you shade it with your pencil, you'll see how it gets darker in a certain region. That's why I use arrows. That's why I wind up using arrows. It's a little bit cleaner.
Because if you take 0, you got 1, so 0.
They're both dotted because it's just a less than. If it was less than or equal to, it would be solid. That was those simple rules from way back when. So it's been a while since we've done that, huh? Yeah. Okay, so maybe I assumed you guys remember more of this than you do.
I don't even remember doing it. Yeah, whenever X is not true,
Okay. Look at this. Let's try another one. We're going to graph 3 equations on one grid. So you have x is greater than or equal to 0, y is greater than or equal to 0, and negative x plus 2y is less than 8. So if you start it out, x is greater than or equal to 0. When you have x equal a number, is it a horizontal or vertical line? It is a vertical, right. Where?
0.
0. So there's my x equals 0. It's solid because it's greater than or equal to. Which side of that line are numbers bigger than 0? To the right or the left?
Right.
Definitely.
So right now I'm going to start to use arrows. It becomes a little bit cleaner if you just have an arrow pointing direction. Y is greater than or equal to 0. And which way is it pointing?
Up.
Up. So right now, everybody okay by saying I have a first quadrant problem? Because the shaded overlap would be just in the first quadrant. Okay. Now I want to pick out my other one. In my other problem, I have negative x plus 2y is less than 8. Can I do cover and solve?
Yeah.
All right, what's your y-intercept? 4. What's your x-intercept?
-8.
Negative 8. Is this one going to be solid or dotted?
Dotted.
Does that line go through 0, 0?
We shall find out. 0 is less than
Is 0 plus 0 smaller than 8?
8. Yeah.
Yes. So now if I'm coming through my shaded region, my overall overlap would be in here. It's bounded by the y-axis and the x-axis and that little area. Okay? That's how we're starting to create these boundaries. These boundaries are intersecting each other here and here, and it's just open through infinity going that direction. Okay. And now, Michael, I know this is what you're about to say. Shouldn't that be an open dot there? Yeah, I know what you mean. But yeah, that's where you're getting that open dot idea.
Yeah.
I don't know what it is.
So how do you know what side is
Whatever one is 0, 0. You'll see how we're getting to it. All right. Yes, ma'am.
I know this is happening.
Hold on.
If the last one was like, because what if you shade it out?
That wouldn't have changed it that much, even though,
It doesn't matter. If you did that, 'cause I see what you're saying, because, yes, you would have shaded all this down here as well. But since you're looking for your overlap, your full overlap, you start to realize that you only have to worry about where they're all being.
No, we don't know that Wisconsin would have that free.
Okay, but they would have to.
Shh, guys, come on. Okay. How do you make a boundary out of this?
Four of them?
They match in a little bit.
Yes.
Yeah, what she said.
So we have x is greater than or equal to -2, x is less than or equal to 5, y is greater than or equal to -1, and y is less than or equal to 3. Now, since this is all done in single variable, it's a whole bunch of horizontal and vertical lines. Do you agree? So, thank God basketball's over. You guys can pay attention. X is greater or equal to -2. Where do I apply it?
X, 2.
Is it horizontal or vertical? Vertical line? In which way is it pointing? Right. So I'm just going to put a couple arrows going that way. X is less than 5. Another vertical line at 5. Convenient. Which way is that one pointing?
Left.
Left. So right now, you have this bounded region between 2 and 5. Y is greater than or equal to -1. Horizontal line through. Which way is it going? Up. And then y is less than 3.
Down.
And it's pointing downward. So you have this overlap region then that created a rectangle. Okay. Now, what you're going to start to be able to do is find all the corners. These are easy because it's set up as a rectangle. And you're just talking about your ordered pairs. Okay. For example, this one would be at -2 and -1. This one's vertical at -2 and what was that, 3. Okay. It's very easy to get your ordered pairs from your horizontal and vertical. The reason why I'm talking about these ordered pairs is because when we get into this 3.4 stuff here in a second, is that those are going to be test points. We're going to use these things as test points to fill in like a constraint. You're going to look for maximums and minimums given a constraint part. Okay? And I'll show you how that works out. But the idea here is we're just doing some very rough sketch graphs with shaded regions. So you're using slope-intercept formula, you're using quick graphing, and test points. Okay? Not so bad? No. So, let's look at. Oh yeah, do this one first.
That's me.
I know.
See, it throws you off guard, doesn't it? Picture of you just shows up there. Hope everyone looks at you.
She's playing
sign
now.
it.
She's playing now.
That's true, she is playing. That's better name.
That's something I would do.
I spelled it right, I think.
Why is he wearing like?
What?
Hey.
No, it just kind of like, there you're going.
There it is.
Oh, it is face.
Oh, did you do Hannah? Because someone else.
Maybe.
Oh my gosh.
Maybe I'm just gonna play girl soccer.
You can grow your hair out.
Yeah, I'll take that.
And you gotta,
Showgirl
and you gotta
down.
be good at soccer.
That's true. I can't do this.
Mac was just on.
Oh, Caleb's face on the ball.
Oh,
I didn't see that either.
Don't need it. In 3.4, when we get into this, what we call linear programming, we take these ideas of quick graphs, and we're looking for these boundary regions. We're going to look to figure out specific ordered pairs where everything intersects. And it deals a lot with systems of equations, solving for x and y, given two equations, and quick substitutions. You're going to find that you're going to use a lot of algebra that you forgot, that you probably forgot about. But it's not going to be bad. Bless you. A lot of times in these types of constraint problems, you're going to notice some of the quick things they give you some, as far as information. Notice the first two parts they give you. X is greater than 0, or greater than or equal to, y is greater than or equal to 0. What quadrant does that mean this is working in? First quadrant. First quadrant. You can handle it. All right. You want to know with first quadrant problems. So when you do that, a lot of times you know that you're going to be just first quadrant. But when you look at the second parts of the problems, notice how you have a negative intercept at some value. Everybody see that? So what I'm going to do, just for argument's sake, is just extend it out so that way I can see what direction my graphs are going to go. All right? You're just kind of preempting it up a little bit. I mean, if you wanted to make the 4 square, go for it. It's fine. You'll start to see when you need to and when you don't. So we know this first quadrant problem, so I'm just going to put an arrow here and here. Are we okay with that?
Yeah.
Now I'm going to do my quick graph. I have a y-intercept of
5.
and an x-intercept of. Okay, so 5 is here. Negative 15 is here. When I connect these two, it's solid. I'm doing that. Everybody okay with that? Now, I have to test it to know what direction it's got to be shaded. Where am I going to test it at? 0. What's 0 plus 0? 0. Very good. Is 0 smaller than 15? Yeah. So this one is shading downward. I know it's still going this way and this way. So in this case, I don't need to worry about the tail to the left of the y-axis. Right that? Okay. Do the same thing with your quick graph for the 2x plus y is less than or equal to 12. I have an x-intercept at
6.
and a y-intercept at 12. So here's 12. And here's 6. Everybody notice how I'm not even marking them off?
Yeah.
Is it okay that I do that? Absolutely. Now, again, 0 plus 0 is it smaller than 12?
Okay.
Yes. So you wind up with this bounded region here. And I didn't show it. Everybody see that bounded region in red?
Yeah.
Now you know 3 of the 4 ordered pairs that's been created. You have the origin at 0, 0. This one is at 6 and 0. This one is at 0 and 5. The intersection there is the intersection of those two. Do you remember how to set up that problem? You'd be surprised, you probably do. What happens here, in order to figure out where 2 lines intersect, you are going to solve the system of equations. You're going to set up, let me flip this to a double page here. You'll set up negative x plus 3y equals 15 and 2x plus y is 12. You're going to solve a system of equations here. And when you solve the system of equation, you can get rid of the less than or equal to or the greater than or equal to symbols and just use equals. Because it's where they intersect, so you have to get an equal value there. Okay. Now, there's multiple ways of doing it. You've got linear combinations where you multiply things together and add them, or you can use substitution. Substitution works really nice when you have a variable with a coefficient of 1, or a variable you can get by itself really easy. In this example here, I would almost take the first equation, well, just move the x over and subtract the 15, and say x equals, well, yeah. If I move the x over here to the right, I add x, and I can subtract 15 to get x by itself, so I have 3y is, 3y minus first Tuesday. What I'm doing there is just getting x by itself. So now I can take it and substitute in. So I take this value here, and I substitute it. Remember that vaguely?
Why? April 7. That means last week was the first Tuesday of the month because there were sirens in Portland, and my mom was like, "Is that April 7th?"
You know what? I heard it
First. They actually, on every Tuesday at NIU, they do it.
I heard it somewhere in Wisconsin. It was really weird. But it was like 11:30 out on Wednesday. The sirens were off and it was 60 degrees. I'm like, oh, okay. Anyway, so what happens here is you do this. 2 times 3y minus 15 plus y is 12. And you're going to solve for one of the variables first, and then get the other order here. So we have 6y minus 30. Huh? Oh, she's ahead of me there. Plus y is 12. 7y is 42. Y is 6. The algebra part here, resolving stuff out, shouldn't be that bad. Well, what happens now is that we know what the y-coordinate is at this ordered pair. The y-coordinate is going to be at 6. And the x-coordinate will be, well, all I do is substitute back in. What's 3 times 6? 18 minus 15? 3. So by using this system of equations here, we're able to solve for x and y at 3, 6. That gives us that missing ordered pair. Okay? We're figuring out where these guys intersect. It's not always going to be clean. You're going to have fractions and things like that. It's not always going to be a clean value. All right? And that's the other reason why I don't give graph paper. Because what's the point? Well, there's no reason to use graph paper because it's not as accurate as solving algebraically. Solving algebraically is the easiest way to go. Okay? Question on that? So that means we can do the following. We're going to use what's called a constraint. We're going to find the maximum and minimum of the objective function given to us at that value of c equals 3x plus 4y. This is your given. For right now, this constraint, this objective function, what you're trying to do, is going to be given to you. When we start to build into more of the word problems tomorrow, you'll develop your objective. But it's going to be pretty easy to tell. You're going to want to maximize profit. You're going to want to maximize sales. Things like that. It's going to be very easy to figure out. But for right now, it's going to be given to you. And it's always given as c equals 3x or whatever. That c value stands for objective. They give you these constraints. And the constraints are going to be a list of some inequality problems. In this case here, let's just start with something easy. We're starting with x is greater than or equal to 0, y is greater than or equal to 0, and x plus 8 is less than or equal to 8. This is a first quadrant problem. Are we okay with that?
Wait,
My- How did I figure that out? Right here, when x is greater than 0
Oh, okay.
and y is greater than 0, that just means it's first quadrant. And I also noticed that my third equation here is x plus y, and my 8 value is positive. I know that I'm not going to have any negative intercepts, so I know it's all going to be first quadrant. What's your x-intercept?
8.
What's your y-intercept?
8.
Okay, so we'll say it's here and here. That's a solid line because it's a less than or equal to. What's the test point I'm going to use? 0, 0. Is 0 plus 0 smaller than 8? Yes. So what we've done is we've found a bounded region created by a triangle. How many ordered pairs do we have for this problem? How many of them do we have to test to figure out a maximum or minimum? 3. You use the 3 ordered pairs to test in your constraint function to see if it's a maximums or minimums. Right? So what you do is you take your constraint, which was c equals 3x plus 4y, and you're going to take your ordered pairs, 0, 0, 8, 0, and 0, 8. And you substitute in. What's that, 24?
Yeah.
Let's see what I did. By listing the 3 ordered pairs out and then just substituting in directly, I'm able to see now what ordered pair is my minimum and what ordered pair is my maximum. Where's my minimum? At 0. So what I do here is this. I just label it my minimum. And which one's the max?
32.
32, and this is my max.
So what does the 3 and the 4 make?
What's that?
The 3 and the 4 and the...
It's a given part, Michael. It's just given to you is which of the ordered pairs by this bounded region creates the maximum or the minimum value at this constraint. The constraint functions change. Okay?
So you just need to find the maximum.
Yep.
So for one, like, for an easy graph like this, you could ideally not actually graph.
Correct. But I want you to get the habit of it because they get more complex. Because eventually you have like 4, 5, 6 of them in there. That would be built out of the word problem that you have to understand. Yeah. Not that scary, I'm hoping, right?
Well, this one, this one.
Let's do one more. We got time to do one more, right?
Yeah.
Let's do one more. And I'll give you a few of these to try today. We've got x is greater than or equal to 2. X is less than or equal to 5. Y is greater than or equal to 0. And y is less than or equal to negative 2x plus 12. And notice how you want to find, it's asking you just to find the maximum value of the constraint of c equals negative x plus 3y. So that constraint function changed. And it changes. All right? Greater than 2. Less than 5. But y is greater than or equal to 0. So I can actually get rid of these guys down here. We okay with that? Basically, I have an open cup, if you will.
Why are those ones dying?
Why do they die? They're dying because you have a bottom. You have the bottom at
No,
y.
why aren't the ones drowning?
It's greater than or equal to. when you're equal to, you're solid. When you're just greater than, you're dotted.
Okay.
Most of the constraint problems that we deal with is are going to be less than or equal to, greater than or equal to.
Okay.
It's very rare we have just a dotted one in there. Okay. And now it's just a matter of plotting through my y equals negative 2x plus 12. That's slope-intercept form. Where's your y-intercept? 12. So we go down to right 1, down to right 1, down to right 1. I think I should have probably counted that off because I may have messed this up. Yeah, that's pretty close. So we're down to right 1. That's an 8. It's doing this. Sorry, my line looks awful. But what's not so bad with this case, since those both x values are vertical, you can find that y value really easy, where that diagonal is going through, can't you? So it's not that bad if it's off by a bit. So we wind up with testing it again. It's bringing it backwards because 0 plus 0 is still, 0 is smaller than 12, so it's still coming back in here, and you wind up with this region. So we have these ordered pairs to look at. We're at 2, 0, 5, 0. This one's going to be at 5, comma what? Well, what's nice that you have that vertical there. In order to figure out the y value, all you got to do is substitute in for x. So what's negative 2 times 5? It's negative 10 to 12. 2. So it's not so bad to do. Ha! Ryan. Math magic. See how I'm vertical at x at 5? That means my x value is 5 when it hits the diagonal. So when x is 5, what's the y value? 5 times negative 2 is negative 10. Negative 10 and 12 is 2. And you do the same thing with the 2 then. So you go up to the 2 times negative 2, you get negative 4, and then negative 4 and 12 is 8. So you have 4 ordered pairs to test. 2, 8, 5, 2, 5, 0, and 2, 0. And you go through them to figure out where your max, in this case, where your max is. I'm running short here. What I want to do. So on page 166, this is section 3.4. Let's go 12 through 20. All right. We'll go 12 through 20 on those. On those problems, it's asking you to find both maximums and minimums. What page is it? 166. Starts on 166. So yeah, we're going we're at the very end of the book. Now we're in the beginning of the book. We're very schizophrenic.
Wait, Mr. Murphy, when we test on this, since we didn't have a test on the last graphing, is that like included?
No, what I do with that trig graphing is that since that was part of the trig unit, I just put it as a regular quiz on that one. This one here, I haven't quite figured out. The linear stuff, I think is going to be a little bit more difficult with the work on because you haven't done them in so long. Whereas we get going into some of the other modeling with the polynomials and the quadratics, it'll get to become a little bit easier. I don't know if I'm going to keep this part as the test later, but I'll probably just quiz over this part and then build the test out of the unit later on. Yay! What did you do for break?